All right. Yeah, thanks for the introduction. So this is the first talk amongst three that follow on applications of Dafny'. And it's joint work with my colleagues at Amazon. So the Fisher-Yates shuffle is a method that goes back already to the 1930s, I believe, that essentially allows you to permute a sequence or an array using randomness such that any permutation is equally likely. And it's an interesting target because it's pretty simple, but also simple to mess up. So if you just get one number off by one, then the distribution won't be correct anymore. So the way it works is, in this example, we're given a sequence of length 10. Then you start on the left, you fix the first element of the sequence, and then you sample uniformly a number between 0 and 9. In this case, say we get 7. Then you fix the 7th element of the sequence, and you swap the two elements, which gives you a new sequence. Okay, and then you start again by moving 1 to the right, so you fix the second element, and now you uniformly sample not from 0 to 9, but from 1 to 9. So say we get 5, and we go to the 5th element, we swap it with with x1, have a new sequence, and so on. Then you go 1 to the right, and this procedure continues until you end up at the end of the sequence. Here we get the 9th element, you swap one more time, and then you end up with the last element, in which case there's only one element, one number to sample, so there's nothing to do. And that leaves you then with a permutation from the initial sequence. And in this paper, Extended Abstract, we sort of described how we implemented the Fisher-Yates shuffle in Dafny' and how we prove it correct. And even though for this case things are still relatively simple, I think it's a nice blueprint for more complicated methods that use randomness in Dafny'. So the way we model randomness in Dafny' follows a perspective taken by Joe Hurt in his PhD thesis. So essentially a randomized algorithm or a sampler from a distribution D that takes values in a domain V would be modeled as a transformation that takes as input so-called bit streams, which are essentially infinite sequences of Booleans, and then transforms that into a sample or into a value in this domain V. And then you say that such a transformation truthfully represents a sampler from a distribution D if this equation here is satisfied. And I won't describe that into too much detail, but essentially what it does, it transforms the correctness statement to a statement about bit streams, okay? So you have this mu, which is a probability measure on bit streams. And that's essentially what's happening here. So we have a probability measure on bit streams, and the correctness is transformed to statements about that. So to make that more concrete, so how do you model a simple coin flip in that framework? So you would take a bit stream as input, and then you return a value in the domain of Booleans, which would be the V in the previous slide. And this transformation would sort of truthfully represent a uniform sampler from 0 and 1 if the measure for the set of bit streams that map to true is the same as the measure of the bit streams that map to false. So both have the probability 1/2. And one way to implement that would be just by returning the first value in the bit stream. So on a high level, the approach we take essentially consists of 3 parts that I think a lot of projects follow. So one, we have a functional model of Fisher-Yates, which operates on Dafny sequences and uses this bitstream transformer approach. Then we have a correctness proof of the function model, which establishes that this function model of the Fisher-Yates shuffle has the right distribution. And then lastly, we have an imperative implementation that you would actually execute that we show is equivalent to the function model and operates on arrays. So let's look at the function model. So I've shown you this coin prime, but actually to compose such functions, you would not just return a value, a sample, but you would also want to return the bit stream that hasn't been used yet. So you can use it in the next step. So formally, what we use, and again that goes back to Joe Hurt, is we use the state monad of type bitstream, which if you instantiate it, gives you these definitions. And if you uncurry the definitions, then you would operate between tuples of values and bit streams. And under that view, the return function would be just the identity. And the bind, the multiplication of the monad, would be essentially just a composition between functions between tuples. So it's pretty simple, and it looks a bit more complicated because we curry it essentially. And if you take the previous coin prime, then you can extend it to this definition by not returning just the first element of the bit stream, but also the remaining bit stream, which is shifted by 1. And more generally, randomized functions would be randomized functions that take an input of type S and return something of type T would be functions that take an input of type S and return herd of type T. Okay. Sometimes these are also seen as Kleisli morphisms for a particular monad. And in the example above, the type S would be just empty, and the type T would be bool. So to speak about the correctness of the implementation, we formalize this probability space on bit streams. Concretely, we assume that there are two elements, the event space and the probability measure, which assigns to a set of bit streams a real value. And we assume that these two constants, which are not defined concretely, they're just abstractly, that they form a probability space, which this axiom here captures. And I won't go into the definitions of the predicate, but it follows sort of classical probability theory. And then then we axiomatize the existence of a uniform sampler that returns values between 0 and n. And this is indeed a uniform sampler if, for any I between 0 and n, the probability that that the probability of all the bit streams that under H map to I is 1 over n. Okay, and that's what I was talking about before, that everything gets reduced to measuring the probability of these sets of bit streams. Okay, and then having assumed this uniform sampler, we can lift the definition to a functional definition of Fisher-Yates. First, we lift the definition of sample to a definition of interval sample, which is straightforward. And then the actual implementation follows the example I showed you in the beginning. That is, first we sample between I and the length of the sequence. Then we take that element, swap it, get a new sequence and a new bit stream. And then we have a recursive call that goes on with the new sequence, the new bit stream, and increases I by 1. And that's the recursive call, and that continues until you hit the base case, in which case you return the sequence. So let's look at the correctness proof for that. So essentially, that is the lemma that we have proven, and what it says is so it has two arguments: a sequence, the initial sequence, and then an arbitrary permutation, which is captured by the second requires clause. So a permutation means just they have the same multiset. And we also assume that the sequence doesn't have any duplicates. And then it's well known that there are factorial of the length of the sequence many permutations for a sequence that doesn't have duplicates. And then the lemma really just states that the probability such that you get this arbitrary permutation P after using the Fisher-Yates shuffle will be 1 over the factorial because there are that many permutations. And again, you measure the probability of this set E of the event that is a set of bit streams. And the actual proof efforts, so we don't operate on the lemma directly, but we establish a slightly more general lemma which has an additional parameter I, and otherwise has the same signature. You just need to figure out sort of the right spots to add the more general component. And the reason we do that is that it allows us to do induction over that lemma, a recursive call. And then you deduce the other correctness lemma that we actually want by just instantiating this one with I equals 0. And the interesting part is that the proof of that more general lemma, which essentially reduces to using two properties that we assume about the uniform sampler. That is one, something called weak functional independence, and two, measure preservation. And I won't go into details, but independent functions, so the independence here refers to independence in the sense of probability theory, which says two events are independent if the probability of their intersection is the multiplication of the probability of the individual events. And measure preserving is essentially what you can see here. And yeah, these two assumptions are sound by previous work, and they essentially they're sort of at the heart of the proof. All right, so in reality, we won't use the functional model, which assumes this infinite stream of bits, but actually we use an external source of randomness. That is, we assume access to an external uniform sampler, which is assumed to correspond to the functional model in the sense that is shown here, the ensures clause. So you have access to some sort of internal bit stream that the imperative implementation modifies. And it does that in this way, which is a bit hard to put into words, but you can see the old keyword here. And yeah, so we assume that on the level of uniform sampler, and then that allows us to lift that assumption again to the correctness of the full Fisher-Yates shuffle, where the correspondence to the function model again is captured as this ensures clause. And the actual implementation is very similar to the functional one, but you operate on arrays, and it's a method, right? And you modify this internal bit stream. And the proof of equivalence uses some appropriate for loop invariant and some assertions that I have omitted here. And yeah, so we can compile the Fisher-Yates shuffle to target languages if, one, the Dafny compiler compiles to that language, and two, the target language offers us an implementation of this uniform sampler, which a lot of languages obviously have. And we have that, I think, for 3 languages in the framework right now. All right, to sum up, we use 3 assumptions. One is that there exists a probability space on bit streams, which is something that Hurt has shown, and that was independently proven. And then we assume the existence of this functional model of the uniform sampler, which we then lift, and an external method sample that implements it and corresponds to that functional model. And even though we sort of draw the line of axiomatization on the level of uniform sampler, you could also go a bit lower by just assuming a coin flip, so uniform 0 and 1, and then lift that to define a uniform sampler. And again, it's well known that this works, but here we have sort of drawn the line a bit higher because of simplicity for the proofs, but also for the efficiency of the actual shuffle, because it's, instead of defining your own uniform sampler, it's easier to use an external one already instead of lifting the coin flip. And then finally, we actually worked over Dafny's bounded int32 type rather than over ints because we wanted to compile to Java's int and not big integer. But we made a change later, but there was almost no proof overhead by that modification, which was interesting. And yeah, with that, if you're interested, there's a GitHub repo and the extended abstract of that of the workshop. So, thank you.
Thank you. Are there questions? Yeah.
Thanks for that. Historically, when we've tried to use reals in Dafny, it's been very unstable. Did you run into that anywhere, or how deep were the real properties you were proving?
So we did not run into that. There was a this is actually a broader framework, and I think we just used a sort of discrete version and not the continuous one. So we avoided that there.
Okay, maybe one final question.
Yeah, maybe I didn't quite understand how you managed to get, like, you started from a bit stream and you gave an example of getting a coin flip from that. But if you wanted to get, 1 out of 3 or 1 out of 5, then you have to do some rejection sampling or something like this in order to get uniform distribution on that. Was that implemented as part of this?
So that, yeah, essentially you're referring to, on the last slide, what I said is that you could draw the line a bit lower. Like you can start with the coin flip and lift that to the uniform sampler. That would sort of do exactly what you said. Sorry? So there's only termination with probability 1, so you run into things like this. But yeah, here we draw sort of the line a bit higher, but if you go sort of into the history of the repo, you will find actually the implementation of that as well. And yeah.
Okay, I think that's all. We can move on to, let's thank the speaker again.